all the people of 6th IT1 and 2 and 7th IT1 and 2 of St. Joseph. My name is Premchand. I'm an IIT chemistry faculty. Today we are going to have some experimental evidences of some chemicals, their reactions and their results. So first among them, as we already have some of you idea, artificial blood. So for that chemicals required, the first one is sodium fluoride, second one is potassium thiocyanate, the third one is ferric chloride. So when we combine potassium thiocyanate with ferric chloride, it will form ferric thiocyanate with the formula Fe3SCN, and that will be less reactive when compared to the sodium fluoride. You already have idea, fluorine is a halogen which is a highly reactive halogen which can displace the thiocyanate ions from the ferric thiocyanate, and the solution will turn into white color. Actually the color of the blood, as you already have idea, red color. When we combine potassium thiocyanate and ferric chloride, it will form ferric thiocyanate. That ferric thiocyanate, because of less reactive than sodium fluoride, will dissociate into ferric fluoride. Thiocyanate will be displaced out. Am I clear? Okay, now we are going to do the experiment. This is sodium fluoride, and the next one is ferric chloride, and thereafter we have potassium thiocyanate. Each one we have to maintain individual spatulas, and we have to take into 100 ml conical flask or 100 ml beaker. Thereafter we have to dissolve the solution, and after mixing we will see the result. So meanwhile, just have a look at this. Okay, now I'm going to introduce you the magnetic stirrer. Some of you have idea and some of you that don't have idea. Actually, any solution, whenever we combine a chemical into this, we have to dissolve it. That dissolution will take some time. To reduce the time and to make the solution dissolve faster, we use an instrument that is called magnetic stirrer. By using a magnetic capsule, it will stir the solution. It will let the solution to stir on its own. This is a magnetic stirrer with a hot plate also. And the white color capsule is magnetic capsule which is maintaining contact with the plate. And now to make the solution dissolve, all we have to do is that, to take this capsule and to add this one to this 100 ml conical flask, keep it on this stirrer, and you have to switch it on. And the solution will dissolve automatically and with a less time than in general dissolution that was done by us. After completion, we have to bring this. This was completed. Thereafter, this is a forceps. As you already have idea, all we have to do is that we have to pour this solution into a beaker to bring the capsule outside. So this is a magnetic capsule. After cleaning it with a napkin, we have to add this same magnetic capsule into ferric chloride solution. So now see this ferric chloride solution, it will also dissolve like that. So after the dissolution, we'll take this one also outside. And again with the forceps we have to bring this ionic capsule outside. So this is potassium thiocyanate. This also we have to let dissolve, and after complete dissolution we have to take this one outside. Now the reaction takes place between potassium thiocyanate and ferric chloride. See, the reaction is going to take place now. This is ferric chloride, potassium thiocyanate. When we add ferric chloride to potassium thiocyanate, we'll see. The red color solution like this, which is formed by the reaction between potassium thiocyanate with the formula KSCN and ferric chloride with the formula FeCl3. Now potassium thiocyanate, when mixed with the ferric chloride, it forms a compound called ferric thiocyanate with the formula FeSCN. So this is ferric thiocyanate. And now sodium fluoride solution we already prepared. You know that the fluorine is a highly reactive halogen, which when reacted with the ferric thiocyanate, the sodium fluoride will displace as the thiocyanate ions and the resultant solution will be ferric fluoride. What is the compound? Ferric fluoride. Okay, now see this. So this is already prepared sodium fluoride solution. Now see the reaction, how it is taking place. Ferric thiocyanate, sodium fluoride. Disappeared. So this disappearing is due to, as already explained, thiocyanate ions are less reactive than the fluorine. That's why fluorine can displace the thiocyanate from the ferric thiocyanate compound, which is a red color. Now the red color solution has disappeared and now the solution color is white due to the reactivity of halogen, that is fluorine, than the thiocyanate complex ion. Am I clear? Hence proved. Okay, thank you. Thereafter we have another experiment, that is artificial snow with a chemical named sodium polyacrylate with the formula C3H3NaO2. This chemical being acting as a super absorbent, and that's the reason it have a wide variety of applications. If you see Pampers and Huggies, some diapers, they are having the same powder. This powder being super absorbent, when children go for the urine and that will absorb the water liquid content in that, they will feel dry, not as wet. Am I clear? So now we'll see the experiment, how it's going to take place. For that the things we need: sodium polyacrylate, again distilled water, and one different spatula than what we used earlier for the potassium thiocyanate, ferric chloride, sodium fluoride. So this is a 100 ml conical flask with the distilled water, and this chemical name is sodium polyacrylate with the formula C3H3NaO2. This is a polymer and super absorbent. Now we'll see, this is a conical flask, right, containing distilled water. If I inverse a conical flask, what may happen? The water may spill, but thereafter adding the sodium polyacrylate, water will not spill due to the reaction between sodium polyacrylate and distilled water and the formation of something, a substance like a jelly substance, which we call as artificial snow. Am I clear? Okay, now I am going to add the powder to this conical flask. Okay, so see, now this is a 100 ml beaker, and the chemical name is sodium polyacrylate with the formula C3H3NaO2. So what is the nature of this powder? Super absorbent, and this is a polymer. So what happens when we add the sodium polyacrylate to water? That is the reaction that we are going to see. Now see, we have to take one spatula. See how the reaction is taking place. After adding the sodium polyacrylate to water, as I said earlier, it is not an exothermic reaction and not an endothermic reaction, but it is a fast reaction, instant reaction taking place between water and sodium polyacrylate, that is distilled water. Now you see, from one solid substance is coming from the downwards. So that is a jelly-like substance, as we also call it as artificial snow. If you cut the diapers, then you see the same substance in that. That is a property exploited by the sodium polyacrylate in that particular area. Now see, which is about to complete. Now I will show you. Before adding this one, the water may spill right if you invert a beaker, but right now it's not going to. You'll notice it. Just hold on for a minute. You now see this complete beaker with a 100 ml capacity was turned into a solid like substance. There is no liquid in this. Earlier we have water, but right now no water. So that you can see like this. This is artificial snow prepared by the reaction between sodium polyacrylate and distilled water. Hence this is also proved. Thank you, thank you. See this sodium metal with atomic number 11 and atomic mass 23 denoted by A, that is equal to Z plus N, and atomic number denoted by Z, nothing but the number of protons present inside the nucleus of an atom. This sodium being second most reactive metal in the periodic table, it can react with the distilled water and can even blast in higher concentrations. When sodium reacting with the water, there will be a color of flame formed. What is that color? Great. So now see whether the golden yellow flame is forming or not when sodium is made to react with the distilled water. For that, the things we need, a glass container which is already filled with the distilled water, thereafter the sodium metal which is protected in paraffin wax. Know why? The sodium is highly reactive with the water, that's why it is always protected in organic solvents like oil, kerosene and this paraffin wax. So paraffin, in this paraffin wax we have sodium metal. We'll remove that and you will make it react with the water. Now you will see the golden yellow flame. Are you waiting for that? Yes. Okay, then I'll do. Okay, now see this. This is sodium metal which is covered with the paraffin wax to make it not to react with the even moisture content in the air also. Actually sodium is reacting with oxygen present in the atmosphere and converting into sodium oxide with the formula Na2O. That reaction of sodium with the oxygen is known as oxidation. What is that? Oxidation. And now this we'll cut this sodium metal. You know metals possess some shining appearance. What we call that one? Now we'll see whether the sodium having that luster or not. You people may notice this sodium containing the shining appearance, that is called as luster. This luster by time disappearing due to the reaction between oxygen which is present in the atmosphere with a volume 21%. Now that oxygen when reacted with the sodium, it will oxidize and form sodium oxide. As you already know, all metallic oxides are which in nature? Basic in nature. When this sodium oxide reacted with the H2O, it forms NaOH, which is a strong base, also known as corrosive alkali. Alkalis are the bases which can dissolve in water. All alkalis may be bases, but not all bases are alkalis. Some of the bases only dissolve in water. Among them, some bases are used as corrosive and some are used as antacid syrups. Example, magnesium hydroxide and aluminum hydroxide, which are less reactive and can be used in antacid syrup to reduce the acidity in the stomach. So stomach will secrete hydrochloric acid, as you know, to digest the food. That HCl when increase its limit, to control that will take antacid syrup which containing metal hydroxides. Example, magnesium hydroxide and aluminum hydroxide. Now this sodium hydroxide, also known as Caustic soda, why? It have an effect on the skin, that is absorbing the water content from the skin. That is called as causticizing effect. Due to that causticizing effect, caustic sodium hydroxide is known as caustic soda, and even potassium hydroxide also known as caustic potash. Am I clear? Now this is oxidized. You see the appearance disappeared. That shining appearance disappeared. Now we will made it to react with the water which we have here. So now you will see the golden yellow color. Are you waiting for that? Yes. Okay, let me see. This is sodium metal, right? Which is oxidized. That means which done with a reaction with oxygen. Now this Na2O is going to react with the water. See what happens. Now see this. See, we'll have the golden yellow color, the flame color. See that one. I'll show you. Due to this oxidation, now we didn't have that golden yellow flame. Now I'm going to add some more concentration to get that golden yellow flame, and even as I told you earlier, higher concentrations may result in explosion. Why? The reactivity of sodium with the water. That is the only point. Now you will see. So this is some little bit more concentration than what we added earlier. Sodium metal which is oxidized. Now you see what happened. I think so, at least now we'll get the golden yellow flame. So this is what happens when the amount of sodium metal is more in concentration. Now the solution is basic in nature, right? When we use red litmus paper in the solution, the litmus paper will turn into blue color. That indicates all the metal oxides are basic in nature. Am I clear? Okay, hence prove this one also. Can you believe that when we stop the supply of oxygen, as you know, 6th class people know, the last chapter we discussed it, air around us. In that chapter what we discussed it, oxygen is a major element for the combustion, right? Without oxygen, can the red phosphorus glow? But it will. So we'll see that one now. We know about phosphorus. What is the atomic number? 15. Phosphorus have two variants, that is white phosphorus, red phosphorus. White phosphorus is on the other hand quite opposite to sodium, highly reactive with oil. So that's why white phosphorus will be kept in water. And sodium on the other hand is highly reactive with water, that's why it is kept in oils. So now red phosphorus we have now. Phosphorus is in when reacted with oxygen present in the atmosphere, it will form phosphorus pentoxide with the formula P2O5. You know, whatever it is to ignite for combustion, that is a kind of reaction. Oxygen is a major component. Even though if we stop the supply of oxygen to the phosphorus, again by the immediate taking of oxygen, it will glow again. You see, when candle is kept with the inverted beaker, it will stop glowing, and thereafter when we open the beaker also, it wouldn't glow again. But red phosphorus will. That is the highly reactive nature of phosphorus with oxygen. Now we have to take some amount of red phosphorus, put a spatula onto this watch glass. So after, what we have to do is that we have to ignite it with a matchstick. Sorry, we have to lit it with a matchstick. So be very careful. It is, the fume generated by the phosphorus are not at all good. So be very careful. Okay, now listen. See this. With a matchstick, I am going to lit this red phosphorus which is on the watch glass. See what happens. See that. So that fume or phosphorus pentoxide. So what we have to do now is that if we stop the supply of oxygen, it will stop. Until the amount of oxygen it is having, it will glow and it will stop. But when we remove it again, immediately it will glow. That is the nature of red phosphorus with the oxygen. Now these fumes are phosphorus pentoxide, which are not at all good for health. So be very careful. Have the mass. That is the reaction between red phosphorus and the oxygen present in the atmosphere. Now you see, surrounded by us also we have oxygen, invented by Joseph Priestley with a volume 21% in the atmosphere. That oxygen is now reacting with the red phosphorus and forming P2O5. What is the name of the compound? That is the formula. Name of the compound is phosphorus pentoxide. What is the name? Phosphorus pentoxide. Okay, please be careful. Don't let the smoke, don't inhale this fumes. Am I clear? We all people know that potassium permanganate with the formula KMnO4. If that potassium is a positive radical, manganate MnO2 is a negative radical, permanganate. So when potassium is reacted with the permanganate, it forms potassium permanganate. That is a purple color, crystal-like structure. So what we are going to do today, we are going to prepare an unstable compound, which is when reacted with sulfuric acid and potassium permanganate, it will form manganese septoxide. This is 98% pure concentrated sulfuric acid. As you know, the strongest acid among all the mineral acids is sulfuric acid with the formula H2SO4. The reason is when it is undergone with hydrolysis, it forms 2 H plus ions. That is called ionization. In ionization, the more the H plus ions, the more the strength of the acid. Due to the reason it is forming more H plus ions, it is a strong acid, sulfuric acid, which is concentrated 98% pure. Now we have to take this sulfuric acid into a watch glass, 2 or 3 drops enough. So after taking the sulfuric acid into this watch glass, we have to close the lid because you know sulfuric acid is colorless. When it is reacted with the impurities, it will turn into yellow color, it will lose its strength. That's why we have to close the knob when we are completed with the taking process. Thereafter, you know about this potassium permanganate, right? A purple color crystal like powder. When we sprinkle just a few amount of this on sulfuric acid, it will turn into green color precipitate. It is a decomposition reaction. When H2SO4 is made to react with the KMnO4, it will form a manganese heptoxide. Manganese heptoxide. It will turn into complete green color precipitate. So zoom in. It is a green color precipitate. Now, when you know cotton is an organic compound, right? Is containing carbon. So all the compounds containing carbon content will react vigorously with a precipitate, that is manganese heptoxide. What is the name? That manganese heptoxide now is going to react with a cotton ball. This cotton ball will now ignite and the flame will, you will see the flame. So it has to convert into precipitate. Still it is like a solution. Okay, now you see this. This is a cotton ball. That is a watch glass containing potassium permanganate and sulfuric acid. The resultant compound is because of the decomposition reaction forming a green color precipitate. The name of the precipitate is manganese heptoxide. What is the name? So that manganese heptoxide will have made all the carbon contents to dissolve in that. Now this cotton ball containing carbon will react with the manganese heptoxide. Is it going to react? We'll see. See, that is what happens when manganese heptoxide is made to react with all the carbon content compounds. Now this cotton ball containing carbon in that, which were made to react with the sulfuric manganese heptoxide precipitate, it is forming some flames with same golden yellow color like as we see in sodium. That is the resultant. Still the reaction is taking place. It is just like the charring effect of sugar. You know about charring effect of sugar? When sulfuric acid is made to react with the sugar, it forms a black color compound that is called as sugar charcoal. What is that? So that also I am going to show you now. Is this clear? Is this clear? Any doubts? Okay, thank you. Completed. Listen, you all people know that 80% of the periodic table elements are metals, right? Will all the metals are solids? There are some metals which are liquid at a room temperature. The best example is mercury. It is a metal, and you know very well metals are solids. They have close packing of molecules. That's why just 20 grams of mercury is having more density than the same 20 ml of water, even though both are liquids. Now this mercury, I am going to add into this. The nature of the mercury is highly reactive towards the temperature. That's why it is used in thermometers. If you go to a doctor, clinical thermometer containing a steel knob, when your body is made to contact with the steel knob, the temperature of your body will be indicated in the clinical thermometer, right? Now see this mercury. So the metal which is a liquid at room temperature with the name mercury as a common name, hydrargyrum as a Latin name. The symbol derived to the mercury as Hg just because of its Latin name only, with atomic number 80 and atomic mass 200. Am I clear? Okay, thank you. As we discussed a lot of experiments, now I am going to show you something which is weird in chemistry. That is not comes under chemistry, it comes under astrophysics, because a lot of astronauts and some of cosmologists will use this ferrofluid as a fuel in the rockets. As we know, we have gravitational energy on the moon, on the planet Earth in which we are living, right? The same gravitational energy do you have in all planets and all other celestial bodies? You don't have. So to just make their survival possible and to make it convenient for the space shuttles and the spacecrafts and all those in the space, they use ferrofluid as a fuel. It is a solution which, when reacted with a magnet, it will form some spikes. So we'll see that one at once. See, this is a container, empty container. These are two magnets. When we have this container on the magnets, it wouldn't stick to this. But after adding the ferrofluid, it will. Is it going to? So we'll see. See this is ferrofluid. Okay, now the same container, same magnets. This is what the ferrofluid means. So when we remove the magnets from downwards, the spikes become bigger, again and will be normal, the solution. When we go too close to the container, the spikes will form like this. See this. These are the spikes which were produced due to the reaction between iron particles, very minute iron particles present in the given solution. That is ferrofluid, right? So this was invented by NASA in 19th century to use it as a rocket fuel and in space shuttles and all those, where the gravity is zero. Clear? Any doubts? Okay, thank you so much.
A gracious morning to one and all. I am Nazia of class 8th, St. Joseph High School. Today I am going to do an experiment called artificial snow. Now this is sodium polyacrylate. Formula is C3H3NaO2. Now we are going to take this spatula full of sodium acrylate. It is 100 ml beaker which is containing distilled water. Now we are going to add this. Sodium polyacrylate is a best absorbing agent which is used in babies' diapers which keep the baby's body dry. In few moments it's going to turn into solid. It's totally freezed. It's totally freezed. Hence brewed.
Gracious morning to everyone. This is Rehanma of class 7, present here to show a artificial plant. First we had to take 3 beakers of distilled water. This is potassium thiocyanate with the formula KSCN. Remember, we had to take different spatulas. Make sure we had to close the cap out. This is ferric chloride with the formula FeCl3. It is in dark green color. This is sodium fluoride to discolor it with the formula NaF. It is white fine powder. Now we had to add potassium thiocyanate to ferric chloride. See, it is in dark red color. Now we had to decolorise it so that we are using sodium fluoride. We are taking in a conical flask. Hence brewed. Thank you.